Hello, my name is Yusuf Kayra Gül and this is me and my teammates PHYS212 project. Name of the project is Observation of Blackbody Radiation and Flame Emission Spectra of Alkali Metals by using Visible Light Spectroscopy. As the name states, we have observed the blackbody radiation of tungsten filament in an incandescent lamp and flame emission spectra of lithium, sodium and potassium with the visible light spectrometer we built. I will present all experimental setup, calibration and experiment process we conduct and the results later in the video. But now, it's time to understand the theoretical background of the experiment. We have used a couple of concepts and equations to both build the experiment and explain the results. One of the concepts that we used is the Planck's distribution for blackbody radiation. Since we observed the blackbody radiation of tungsten filament, we used Planck's distribution to compare our data with theory. Planck's distribution basically gives a spectrum radiated from an object due to its temperature. As the temperature rises, peak value of the spectrum shifts to the lower wavelengths of light. We tried to observe this effect by varying the voltage passes through the filament. Now we need to calculate the temperature of the tungsten filament. For this, we started with the Planck's distribution, and by integrating it along the whole lambda axis, we got to energy density per unit volume, which is a function of just T, temperature. And then, to find the energy flux density, we multiplied the function with light with the speed of light. Then, since tungsten is not an ideal blackbody, we multiplied it with an emissivity coefficient, and finally with the surface area of the filament, we got the power output of filament. In equilibrium, this will be equal to the power we supply to the lamp, so by voltage and current, it is possible to calculate the temperature. For emission spectra, we intended to solve the time-independent Schrödinger equation using some computational methods for lithium, sodium and potassium. But it was very hard and out of our knowledge, so we used some spectroscopy data tables to compare our data. But the idea behind the flame emission spectra is when an atom is excited using temperature, its valence electrons jump to a higher state of energy where it radiates certain wavelengths of light as it comes back to its ground state. We observed these radiated lights for lithium, sodium and potassium. We used a reflection-diffraction grating in our experiment which diffracts and reflects the light coming onto it. And this is the formula we used to understand how this grating works. Now it's time to see our experimental setup. This is our experimental setup and it can be seen from the image. We are using a black box to minimize the reflection within the spectrometer. The white plate sticked on box is light diffuser which we use to make light more homogeneous before it gets in the spectrometer. Behind the diffuser, at the inner surface, there is a slit formed by sharp edges of two razors. As our diffraction grating we use the CD, and in front of the CD there is a webcam to capture the image of the diffracted light. And now it's time to show you the calibration process. We are using two lasers which are green and red due to their certain peak wavelengths. Now we are using the green laser to adjust the wavelength in the taken data from our spectrometer. After adjusting the green, it's now time to adjust the same thing for red one. As it can be seen by this process, we calibrated our spectrometer. Now it's time to see how we conduct the experiments. First, I will show the flame emission test and then the blackbody test. Now, what you are seeing is the flame spectra test for lithium. As it can be seen from the screen of the computer, it has one sharp peak wavelength due to its emission energies. And now, this is the flame emission test for sodium, and as it can be seen again, it has one sharp peak in its spectra due to its emission energy. Lastly, this is the potassium's flame emission test, and it can be seen again, it has one sharp and strong peak in its spectra. Now, this is the result of flame emission spectra of lithium. As it can be seen, it has a peak at 672 nanometers, and it meets with our expectation, which is at 671 nanometer. And this is the result for sodium. As it can be seen, it has a peak at 588 nanometers, and it again meets with our expectation value, which is at 589 nanometer. Finally, this is the results for potassium, and as it can be seen, it has a peak at 773 nanometers and it again meets with our expectation value, which is 766 nanometers. We could not take any videos during the experiment of blackbody radiation, but I will now present the results for it and explain. This figure shows the blackbody spectra of tungsten filament at corresponding voltages and temperatures. As it can be seen from the plots, as the temperature increases, total intensity increased. Also, the slope at the left of the spectra increases with the increasing temperature. Increase of both the intensity and slopes shows us that the blackbody distribution shifts to lower wavelengths with increasing temperature.